Good morning. So we start today's lesson. We continue our discussion about matrix theory. So if you remember, we concentrated when it came to multiplication. We concentrated a little bit in the previous session about the differences between matrix algebra and number algebra. Okay, so if we go back here to remind you a little bit, after here we had something, as a summary. So we realized that there are some main differences between matrix algebra and number algebra when it comes to multiplication. The first thing, if you remember, two numbers are always multiplicable, but this is not the case for matrices. For having this product defined, I need to have the number of columns of the matrix sitting on the left to be exactly equal to the number of rows of the matrix sitting on the right. Otherwise, this product is not defined in the first place. Okay, so that's one difference, because for numbers it doesn't matter. A times B is always defined, always. Another property is that for numbers, if A and B, which of course always are defined, it doesn't matter if I multiply A by B or B by A, but we realize for matrices this is not the case. Sometimes if B is possible, is definable, but B times A is not defined in the first place. And even if they are defined, there is no guarantee still that this AB is equal to BA in general. So that's another difference. Another difference, if you remember, matrix multiplication does not obey the zero product rule. The zero product rule for numbers tells you that if A times B is equal to 0, you can conclude either the first one is 0 or the second one is 0. But this is no longer valid when it comes to matrix multiplication. I gave you an example of matrices without having even one single zero entry, but we realize that the product is equal to the zero matrix, even though neither A nor B was a zero matrix. This is the third difference. And finally, the last difference is that in numbers, if I have AB equals to AC, and I know that A is not the zero number, I am allowed to cancel this A from both sides by dividing both sides by A and conclude that B is equal to C. And this is called the multiplicative cancellation law. But multiplicative cancellation law in general is not valid when it comes to matrix multiplication. In principle, if I know matrix A multiplied by B is equal to matrix A multiplied by C, even if I know that matrix A is not the zero matrix, still I am not allowed to cancel A from the sides and conclude that B is equal to C. We will see that this condition can be we can have this cancellation law under a little different condition. That condition is not the matrix shouldn't be zero. There is a number associated with the matrix, and that is determinant of a matrix. If the determinant of a matrix is not zero, then this cancellation law is possible. Okay, for the time being, don't worry about that, but you are not allowed to take these rules for granted unless you have a very good reason for that. For example, we realize that the diagonal matrices, if I have two diagonal matrices of the same order, the product of them becomes a very simple formula, and then from that formula we realize that they commute. So this is one important class of commuting matrices. Diagonal matrices are among the important classes of commuting matrices. Okay, so now we continue. Okay, and then after these differences, we started learning a little bit about similarities between the matrix multiplication and the multiplication of numbers. So if you remember, every number multiplied by 0 was the zero number. Here, of course, we have something similar, but because these are matrices, I need to be careful about the order of multiplication. So if A times the zero matrix or 0 times the matrix are defined, then the answer is definitely 0. And there is no guarantee that this 0 matrix that you see here is exactly this 0 matrix. For example, in this example, I have a matrix with 3 rows and 2 columns, 3 by 2, and this matrix has 2 rows and 4 columns. So it is possible to multiply them because these two numbers are the same. But as you see, the answer is the 0 matrix, but this 0 matrix is quite different from the 0 matrix that appears here. This 0 matrix is a 2 by 4 matrix, this 0 matrix is a 4 by 4 matrix, okay? So, but of course, if A is a square matrix, then it doesn't matter in which order I multiply. So this is also another thing to remember. The square 0 matrices commute with every matrix of that order. Of course, on top of that, the answer of the product is also 0. So this was one similarity, more or less, between this and this matrix algebra and the number algebra. Another one was also very important in matrix theory is multiplication by the identity matrix I. Yes. So we also learned that if a number is multiplied by 1, the answer is the same matrix. This is more or less. We have also more or less a similar identity in matrix algebra, and that means that if you multiply a matrix by the identity matrix, it becomes the same matrix if it is possible to multiply it, if the product is defined. Okay, and for that one I actually proved the theorem for you. Okay, so I want to continue the discussion of similarities between matrix algebra and number algebra. So these analogies are very important to have a organized, categorize these things in your brain so that you can immediately use them when necessary. Okay, now we start today's lesson. We start today's lesson by another theorem, which is of course predictable. It's not that hard to predict this. This tells you that if you have two matrices A and B, of course, the number of columns of A has to be equal to the number of rows of B. If that is the case, and alpha is a number, there is no difference between these combinations. So it doesn't matter if you take your first matrix multiplied by a number, definitely it generates a new matrix for you, and then multiply that new matrix from the left to your matrix B. It would be exactly the same if you choose to multiply the number alpha to B first to generate a new matrix for the right matrix, right-hand side matrix, and then multiply A to that new matrix from the left. Or if you want to, you momentarily don't care about alpha, you just multiply these two matrices first in the same order that you are desired, you want to, and then when you found the matrix you multiply it by alpha. And because all of them are the same, so it means that we really don't need to prioritize these operations, so I don't need to have pair of brackets. This is completely a well-defined object. Okay, I don't think the proof of that one is hard, so you can work the proof yourself here. It's very simple. But here, this example, the first example for today, I want you to show this. This seems very trivial, of course. 2a times minus 3b is minus 6ab, but I want you to fully appreciate that if these rules are not correct, then I am not allowed to write something even trivial as this. They might not be true, okay? I'm emphasizing this for those people who are going to continue, I don't know, computer science, mathematics, or theoretical physics in the future, so they will see that there are very strange algebras that you need to work with, so there, you cannot take everything from numbers for granted, okay? Because you cannot say that because 2 times x multiplied by 3 times y, when I was working in simple algebra, it is minus 6xy, so because this is true, this is also true. No, I just want you to understand that if you are facing a new mathematics system, you need to think everything from scratch again, if they are working or not. Okay, why this is correct? For example, we can consider the different scenarios here. One thing that we can say is this. Okay, so for example, let me just justify why this is plausible. So 2a times minus 3b. So what can I do? let me give the role of matrix A to this matrix. Then I will have A multiplied by minus 3B. Yes. And now look here. I have this situation now that alpha is this minus 3, B is the same B, but this A is playing the role of that A. So according to this formula, I can move this alpha and put it next to my matrix A. So I will take this minus 3 and put it here. So let us see what happens. So this becomes equal to, there is a B left alone, and then I will take minus 3 and put it next to 2A, and then I have to close this. So this, from here to here, I am using this theorem. But there was another theorem, if you remember. If I have R, a number, multiplied by SA, I can write it as R times S if they are numbers, and then multiply it by A. This is actually long back, where we were talking about a scalar multiplication. So here I copy and paste B part, but I want to use that theorem here. So then it means that I can write minus 3 and multiply it by 2 and then A and then close it. And now minus 3 times 2 is minus 6A, and then I have B. Again, I can use the last bit of this theorem. If I have a number alpha multiplied by A and then multiplied by B, we don't need to do that. I can just write alpha. So I would write minus 6AB. So you see, for this simple rule to work, for this simple equation to work out, you used this theorem 2 times and another theorem from the previous lesson 1 times. So the truth of this equality relies on this theorem and the previous theorem for a scalar multiplication. So if you don't have them, if you don't have any one of them, then this will not work. So this is very important to see the core of these calculations. Now a very important theorem, and this is good that we are not losing everything. We already lost commutativity, but the good point is that we are not losing distributivity. But you need to be careful here. So let me read the theorem for you, and I want to prove one of these versions for you. And I think it's very good exercise if you do the other ones yourself. So matrix multiplication is distributive over matrix addition and subtraction from both sides. That is, if B and C are matrices of the same order, say M times N. So let me just write these details here for you. So B and C are M by N matrices. We want to show that it is possible if I have the sum or difference of two matrices B and C, and then I want to multiply a matrix M from the left to this, I can distribute it exactly like numbers. I can write M times B and multiply it by M times C. If there's an addition, I put the plus. If there is a subtraction, I put negative sign. For every matrix M with M columns. So let me write this for M is a matrix with M columns, but any number of M columns, but any number of rows. So let me take P rows and M columns. And that is clear why it should be like this, because if these two matrices are M by N, if I add them, it becomes M by N, and now I want to multiply M from the left on a matrix which is M by N. So it means that this matrix should be P by something. Okay? So how should I prove this? First of all, I want to show that the left-hand side is a matrix of the same order as the right-hand side. But this is very simple. Let me just talk about it orally. If I ask you what is the order of the matrix sitting on the left, you would say that B and C are matrices of the order M and N. If I add them, it becomes the same order. And my matrix M is a matrix P by M. B plus C or minus C is a matrix of M by N. So the final answer of this product would be a P by N matrix. So the left hand side, let me write it here not to forget, the left hand side was a P by N matrix. But what is the right hand side? Immediately it is clear. What is M by M times B? M is a P by M matrix, B is an M by N matrix, so it is a P by N matrix. The same is true for this one. Now I am adding two M P by N matrices, so the answer would be a P by N matrices. So these two matrices actually match from order point of view. This is very simple, so I just talked about it orally, but in the real proof you really need to write all of these things down. Okay. Now the second step, which is more probably important, is to consider an element, an entry on the left hand side, and show that that entry corresponds, E is equal to the corresponding entry of the right hand side. So let me now write the proof formally. I would say that let I and j be integers such that I is somewhere between 1 and the number of rows of the resultant matrix, but we learned that the resultant matrix is supposed to be P by N, so it would be between 1 and P, and J between 1 and N. We show that what I'm supposed to show, I am showing that this entry of this matrix is equal to the corresponding entry of the matrix on the right. This we are supposed to show. But then I have to use the definition of the product, that sigma notation, if you remember. So I will start calculating this. M, B plus or minus C, I, jth entry. So do you remember? It's a product. Do you agree with me? This is the product between this. You can imagine this matrix is D and this is M times D. Okay? So what I write, I open a sigma in front. I choose a counter except for I and J. So it goes from 1 and it goes up to the number of columns of this matrix, or equivalently the number of rows of this. But the number of columns here is M, so K goes from 1 to M. And then my matrix M, let me write it with so that with little m is actually unfortunate, so let me write the capital M. And then I start with the I index, but I end it with the let me write it as usual. And then I end it with the counter of my sigma. Second matrix is B plus or minus C. I start with the counter of the sigma and end it with the index j. Now, if you remember, the definition of addition or subtraction is important here. I cannot do anything with the first one, but I can do something with that. If I ask you what is the kjth entry of the addition of two matrices, you would say that I will take the kjth entry of this one, kjth entry of this one, and add them or subtract them according to the problem. So this means that I will take B kj and then add it to C kj, or of course subtract it depending to that one. But now, can I distribute this here? Don't think that is a circular argument. This kind of distributivity is at the level of matrices. But here, if I ask you what is this, this is just one single number. The same true for these two. So it means that I can use distributivity of real numbers over addition and subtraction. Okay? So it is not exactly the same property, but it highly relies on that property of real numbers. Okay, so what happens is MIK multiplied by BKJ plus or minus MIKBKJ. Yes, hopefully I can fit it here. And then I use a sigma property. I have addition or subtraction of two expressions under the sigma notation. We know from the properties of sigma I can decompose it into two sigmas, yes? So it becomes the sigma of the first one plus or minus the sigma of the second one. But can you tell me how can I write this now? Is this combination familiar for you? You see, I have a matrix, another matrix. It starts with I index, it ends with J index, and the middle index is exactly this K. The counter of the sigma and the number on top of the sigma is exactly equal to the number of columns of A, or equivalently to the number of rows of B. So this is actually a matrix multiplication, but which entry? It is M times B, entry number ij. For the same reason, the second sigma is M times, oh, I made a mistake, yes, all the time. Sorry. This is not B, this is C. So this is C. This one is also C, not B. Okay, so the second one would be this. But now, hopefully you can agree with me that this is MB plus or minus MC ijth entry. And we are done. So I started from the left hand side here. I just used the definitions of matrix multiplication, matrix addition and subtraction, and I was able to got that. But it is extremely important to remember that order is very important. In numbers, you can be quite careless. If I want to multiply m as a number by m plus or minus c, I can just write mb. I don't need to be very careful, even though most of the time we write it in order. But if you write something like this, that's completely acceptable, because numbers doesn't care about the order in which they are multiplied. But in matrices, it's very important to pay attention to the order. In other words, if you have your matrix on the left and you want to multiply it, you have to respect the order and write the matrix M all the time on the left hand side. And if you have your matrix N on the right, still you can distribute it if the products are defined, of course, but you have to care about the order. If N is on the right, in the products that you see, the matrix N has to be on the right all the time. And then you remember, any distributive law brings you a factorization law, yes? So you have M times B plus C, from left to right is distribution. But if I want to go from right to left, it seems that I am factoring this M out. And that is also true for matrices. But in numbers, it doesn't matter on which side the common factor is lying. But if you want to be able to pull something out in matrix multiplication, that common matrix should be on the same side of the terms that you are pulling that M out of them. It's important. So here I want you to do, for example, these are simple questions. Let me finish this lesson to this part. Yet I want to teach the new lesson of raising matrices to powers, which is a more interesting topic then. Okay, so let us consider this example. Let A and B be m by n matrices, and let C and D be n by p matrices. Then expand this. Of course, again, there is nothing hard about this example. I just want you to appreciate that you have to use both versions of distributivity here. One version is not enough. I want you to feel about it. So if I want to distribute this, it's like a polynomial. I will never spend time to do it the way that I am going to describe it right now, but for understanding it is crucial. So if I want to multiply this by that, and these matrices are given, the orders are given in a way that all the products are definable. So let me say what we can do. For example, you can consider this matrix E in your head, and then you will face E times C minus D. So I am using the first version, distribution from the left, okay? So what happens, it becomes E times C minus E times D. So I am using distribution from the left. But then E is this matrix, so let us not spend time to write two things, okay? I will, instead of E's here, I put A plus B. So it becomes A plus B times C minus A plus B times D. This is the first version of distribution, the first rule, distribution from the left. Now I want to distribute C here. Can I do that? Yes, because distribution from the right is also possible. Here the same. So this becomes equal to, I am using the second version now. Yes. So it becomes A times C plus B times C, and I have negative. And then I will do the same thing here, AD plus BD. Okay, and of course I can now move this minus sign and I write AC. There is a theorem we could do it. What was that theorem? Do you remember? It was if I have R and I have A plus B, I can distribute R inside. So it becomes RA plus RB. Here my R is minus 1, so it means that I can do that. So this becomes AC plus BC, and then I have minus AD minus BD. Okay? Of course, I will never do something like this, but I want you to understand, if you give me this, I just act like polynomials. I am just describing here why it is possible to act like polynomials. Because, fortunately, we have both distributions, from the left and from the right. Yes? If I want to do it myself, I will just distribute it AC minus AD plus BC minus BD. I don't spend time on it to do it, AC minus AD plus BC minus BD. Okay, and that's the same thing. Please interrupt me if you have questions. Okay, another example, it's important to realize how you can factor a common matrix out. I want to make sure that everything is understandable and you are not making mistakes. This is an example designed for that purpose. So in each of the following expressions, factor out, if possible, matrix A. To make sure that all multiplications are defined, we assume that all matrices involved are square matrices of the same order. So you don't need to be worried about if the products are possible. Okay, so let us just do it one by one. Can I factor matrix A out? Yes, there is a common matrix between these two, and then A here is sitting on the left, A here is also on the left. Yes, so I can factor it out, and I have to factor it from the right. It's on the left, I have to factor it from the left. There is no other way to write that. You are not allowed to a priori assume that these matrices are commuting, unless this is directly given in the problem, or this is among those category of matrices that you have knowledge about their commutativity. But here we don't know. We just know that A, B, and C are matrices. I don't know anything else about them, so I'm not allowed to presuppose that these matrices are commutative. So, is it possible to factor even under these circumstances? The answer is yes, provided that you decide to factor from the left. This is the only way that you can write that. So, number 2. Is this possible for number 2? Yes. I have A on the right, so I have to respect the order and I have to factor A from the right. This is again the only way that I can do it. What about this one? Can I factor something out? Even though A is a common matrix involved, But here A is on the left, here A is on the right. So no ways. There is no way that I can factor it out unless I have extra information about commutativity of these matrices, for example, which I don't have here. So it means that I would say not possible. Okay, for number 4, what can I do for number 4? Do you have any idea? Can I factor something out here? Yes, exactly. Because of the rules that we learned is that I can imagine this problem in this way. Instead of A, I can write two things. I can imagine two things because they are A square matrices. This is A times I, this is also A. Which one is suitable for this case? If I choose this one, then I will have problems because then here A is on the right, here A is on the left, I cannot continue. But I have another option, yes? So instead of A, I decide to write A times A, even though I times A is also correct, but if I do that, I will not be able to continue. Now I see that A is sitting on the left, so it becomes A and B plus I. So be careful. If you just naively pull A out and write B plus 1, this becomes nonsense, yes? Because B is a block of numbers and 1 is just one number. In principle, we cannot add them. So be careful. This I should be here. Okay, and let us go to the next one, number 5. So what can I do? Do you think that I can factor something out in this number 5? Yes? Yeah, 3 times identity, exactly. So in which order first I write it? I would write BA because now A is on the left. So instead of A, I write 3I times A. Now A is on the right, sorry, A is on the right, I was mistaken. So A is on the right, so I write 3 times I times A. But now if I want to factor, I have to factor from the right. This is now the only way that you can do it. So appreciate these small differences. Okay, but for example number 6, now you know what to do. It's possible again. I have AB minus 3A. So this time I write AB, but instead of 3A, I would write 3AI. Because now I want to have A on the left to be able to factor it out. And I have to factor it out from the left. So it becomes minus B times 3I. And by the way, if you want to be very pedantic to understand to everything, in principle, what you need to do, you need to write AB minus 3A is equal to AB minus 3. Instead of A, you write A times I. And then do you remember there is a rule that minus 3AI can be written as A times 3I. And now A is on the left, I can pull it out. So if you really want to be very strict, every step should be written, you have to write everything like that. But anyway, this is guaranteed that we can do that. Okay, now let us go to these two last numbers, number 7 and 8. So what can I do on number 7? Let me just rewrite it again, I have enough space. So A, C, D, A. Here you see that A appears 2 times in each item, yes, in each term. And then that is good because here it appears on the leftmost one, and this appears on the this appears on the rightmost one, and the same is true for these two A's. So I can pull these two A's from the left and these two A's from the right. You can do it simultaneously to save time. So what I do, I open a pair of brackets, I put an A on the left and an A on the right. So this A is pulled out from the left, this pulled out from the right. So what is left here is B. And here this A is pulled out from the left, this pulled out from the right. What is left is CD. So that is the only way that I can do it. For example, let me change my color. If I have this situation, A, B, A, and then I have minus A, C, A, D. In this case, what can I do? How many factors I can pull out? Can I pull out again two A's?
You can only pull out in left
A, exactly. You see, even though still I have two A's involved, but only one of them is in the right place. So here I can pull one A out, it becomes BA minus CAD, nothing more. This A is imprisoned, actually, is captive, is taken captive with these two CDs. I cannot do that unless I know something about commutativity of one of these matrices with A's. So might be I can do it. Okay, so be careful. Number 8, do you think, there are two ways I think we can do in number 8. Do you agree with me? So one scenario is to imagine instead of 4A, I can write 4AI. Another possibility is that I can write it as 4IA. If you interpret this in the first version, this A and that A is on the left. Pardon? May you speak louder? I cannot hear you.
For number 7.
Yes?
It is ACBA, not ACAD.
With this one, are you talking about?
Yeah.
So if I multiply this, no, that's correct. No, this is a different story. This I just wrote it from myself.
Oh, okay.
This is not one of them. This is the answer. This is why I wrote it with a different color.
Yeah.
I realized that this might be something that worth mentioning. This is why I wrote something new. This is not the same problem. The answer to this is here. Okay, now can I factor something out from this one? For numbers, you shouldn't be worried. I can factor numbers out because numbers can float around, yes? Because alpha A times B is the same as A times alpha B, and it is the same as alpha A times B. So you don't need to be worried about numbers. This number cannot keep this A as captive, okay? You cannot imprison this A because 4 can float around. Okay, so what I'm saying is that if I interpret it in this way, I have 2A on the left and I have 2A here on the left, I can factor 2A from the left. And then what is left for me, from the first term I have BA, from the second term I will have 2I. This is one possibility if I want to do this. Another possibility is interpreting the same idea, the same expression in this way. But now you see that A and A are now on the right, so if I want to pull A out from here, then I have to pull out it from the right. But of course 2 and 4 are also common, they have also common factor. These numbers are not important in which direction you are pulling them out, so usually we pull them from the left. So it becomes AB and then plus 2I, and then I have A on the right. So double check. If I multiply everything inside, it will give me this. If I multiply these two inside, it will give me this. So for number 8, according to the problem that you are solving, might be one of them is useful, the other one is not useful. But when it comes to correctness, both of them are correct. Might be one of them is useful, the other one is not useful from the problem that you are solving at that moment. Any questions? Okay, So let us go to this example. I want to wait a little bit for you to solve this problem for me. I just paused the video. It's a very simple problem. Okay, do you have the solution now? Or at least a way to the solution? Yes?
We first factorize A and B out.
Yes?
And
Yeah, so this is actually a very particular problem. Yes? Because, let me read the problem. Yes, you are right. So let A and B be square matrices of order 2 such that the product is this one. Of course, one way might be the case that can I find A and B in... I haven't thought about that, by the way, because if the product of these two matrices is this one, can I really determine A and B? Exactly. We can also think about that, because in that case I have A, B, C, D for matrix A, and then I don't know, E, F, G, H, F, G, E, F, G, I for this matrix, and if I multiply them, so it means that in general I have 8 unknowns, and if I want to equate it with that, there are more number of unknowns than the equations, because by equating this to this I will get 4 equations, but I have 8 unknowns, so I have degrees of freedom. Might be that's also a good way to think about that. I haven't thought about this, but even if this is possible to find, this is clear that this is not possible to exactly find those numbers unless this is a very particular situation, which I don't think so, because for example for the first one you get AE plus BG, this should be equal to 1, and this system is also not a very simple system to solve. But that's what I'm saying. Finding matrices A and B, even if possible, it's really tedious. And that's a good idea to think about that. If you can cook up some matrices A and B with that property and see that what do you get these at the end. Do you get the same answer? In principle, you should be able to get the same answer if you can cook up those matrices, because that depends on the product of A and B, nothing more. But the way that Alex actually proposed, and this problem is designed based on that idea, is that, of course, this is one of those problems that are not very easy to detect. These are very special cases, because who knows what will happen when I add them, but if you're a little bit observant, you realize that there is a pattern going on. So even though I don't know A, but I know that in this combination A appears on the left, and in this combination B appears on the right. So at least I can factor A from the left and B from the right, and to see what happens. Okay, I have 2, -1, 3, and 5 left from the first term, and then I will have a -1, 1, -3, -4 left from the second one. But now if I add these two matrices, I am lucky, because 2 - 1 is 1, -1, 1 is 0, 3 - 1 - 3 is 0, and then it is 1. So this is a very particular matrix, so which means that I really don't need to worry about that. Assume that this is a very generic matrix like 2, 5, 9, and 10. Okay? Then I think that would be a dead end for the solution to this problem, unless we can calculate A and B explicitly, which doesn't seem very promising in this problem. But this is one very special case, that this turns out to be the identity matrix. So this is nothing except the identity matrix. Okay? I have been a little bit careless here. The reason is that when you are dealing with the product of more than 2 matrices, I have to talk about associativity first and then go back there. Okay, so that was my flaw. You see, whenever this comes to this, it's very hard to differentiate between these things. Here I have 3 matrices being multiplied. Yes, so definitely, and there are no brackets around them, but there is no guarantee that the answers are different. But here, of course, you can say it doesn't matter if I want to multiply them in this way. If I multiply these two first, it becomes A, then multiplied by B. Or if I consider this 2 first, it becomes B and then AB. So you see the answer is AB. And the problem is designed in a way you don't need individuals individual matrices A and B, you need the product, and the product is given in the problem. So this is the answer. Yes, I don't really consider this a very nice problem, but actually we were able to solve it finally. Okay, so this is also one example, and now let me finalize this lesson by the final theorem, and I have forgotten to write. This is associativity. Okay, so, and again, this is very good. So you see, we are not losing everything. We're just losing commutativity, and of course there are some consequences, very non-trivial consequences of this loss, but we still have associativity. I want to prove it here for you, and we had a distribution and similar ideas. Okay, by the way, I want you to appreciate that is not trivial at all, because you know matrix multiplication is fairly complicated operation, and if I have three matrices, if I multiply these two matrices, I get a totally different matrix than the primitive matrices A and B. And it means that essentially I am multiplying a new matrix by C. Here, if I multiply B and C, the same story. This becomes a quite different matrix in general, and I'm multiplying that new matrix from the right to A. I want to say that the answers are the same. It's not trivial at all. But we want to show that this is the correct formula. So, for here, let us consider these matrices, because I want to have these products being possible in the first place. If there is nothing, if it is not possible, so how can I talk about them? So this is why I have, for example, written A is an M by N, B is an N by P, and C is an N P by Q, so that this product in this order is defined. Okay, so first of all, I want to show that this matrix is equal to this matrix. I have two responsibilities for that. I need to show that the order of matrix on the left and the order of matrix on the right are the same. And then after I am relieved from that point of view, I need to show that every entry called ijth entry of the matrix on the left is equal to the ijth entry of the matrix on the right. If I can show that, then I am done. Okay, so let me just be patient a little bit and write it properly. So I have A, B, brackets around them, and C. What is the order of A? The order of A, according to the problem, is M by N. What is the order of B? It's N by P. And what's the order of C? It's P by Q. Okay, so this gives me N by P, and then these two are the same, so this will give me finally M by Q. And hopefully you agree with me, the same story is true for the right hand side. Yes, you can check it yourself. It's very simple. The same, it doesn't matter how you prioritize them, the product would be at the end M by Q. So from order point of view, everything works fine. But now I need to look here. What is the final answer? The final answer is M by Q. So I would say that let I and J be integers such that I is between 1 and M and J be between 1 and Q. We show that, let me save space as much as I can, we show that A times B first and then times C, ijth entry, is equal to A times BC first, ijth entry. That's my goal. Now, of course, you realize probably associativity of real numbers will play the vital role here. And you will see that's the case. Okay, so let me start from the left hand side. So the left hand side, let me write a little bit smaller. Okay, you can imagine this as a matrix D in your head, and then you have D times C ijth entry. So I need to open a sigma, choose a counter for my sigma. It goes from 1 up to where? Can you tell me? by looking at these items. Up to where? I want to write something for this. I am considering this a D matrix.
Up to P.
Up to P, yes. Yes. Because the number of rows of C is P. So it goes up to P, and then the first matrix, which is AB matrix, it starts with I, ends with K. The next matrix starts with K, ends with J. Yes? But now I have another product to take care of. So what I have to do, I have to write this sigma. K goes from 1 to P. If you don't mind, let me put a pair of brackets here and then C, K, J. Yes? Now I want to write another sigma here which represents this. So I open up a sigma. I have to choose a counter. I'm not allowed to use I. I'm not allowed to use J or K because I have already reserved those letters for a different purpose. So what I do here, for example, let us choose S. S definitely goes from 1, but up to where? Up to where?
Up to N.
Up to, yes, N. Thank you. It goes up to N, and the first one, it starts with what? Can you tell me? So let me write them. The first one is A, the second one is B. A starts with what and ends with what? The same for B. Yes? A starts with what is, so have you forgotten? What A, do you know what should I write for A starting index? Yeah, it should be I. Why you doubt about it? Because this is I and this is K. So it means that A should start with I, B should end with K, and the middle indices are the counter of the sigma. Agree? Okay. Now, can I flip this inside this sigma? The answer is yes, because this sigma depends on S. The counter of this sigma is S. But there is no S dependence for this number. It depends on K and J. So as far as this sigma is concerned, this is a constant number. So I can flip it in. So then I would write sigma. Let me write a little bit smaller. K goes from 1 to P. And then I have another sigma here. S goes from 1 to N. Then I have this situation. Then I have C sub Kj. Okay? And then here I have A, I, S, and then B, K, Sk. Okay? Hopefully it's understandable. And by the way, I really don't, let me clean it and write it properly. I don't need that sigma, that pair of brackets. So let me start from here. So I would write sigma, K goes from 1 to P. What I am doing, I am flipping this C inside. So it becomes A sub IS, B sub SK, and then C sub KJ. And then here S goes from 1 to P. I don't need to put another pair of brackets here because you know that we have already talked about consecutive sigmas. But here this is crucial to put a pair of brackets around them because this is already there and I am flipping this. So in principle I have to find this product first, and when I found it I have to multiply by the coming number. But this is not crucial here because we know that these are numbers and it doesn't matter if I put a pair of brackets here or a pair of brackets around them because multiplication of numbers is associative. So this goes sigma from K to P, sigma S from 1 to P. I would write A alone and I put the other pair in the pair of brackets. Okay.
The second sigma is
N. Oh, okay, thank you very much. This you mean. Yes, this is N. Thank you. And this is also N. Okay, thanks. And now let us see what happens here. Of course, can I pull this A out? Not yet. Because this sigma depends on S. The counter of the sigma is S. This also depends on S. So this is not a constant, so I cannot pull it out. But we learned before that I can interchange the positions of these sigmas, if you remember from previous lessons. So here it means that I can interchange these two and write it as S equals to 1 first, N, and then K goes from 1 to P, and then I will have A, IS, and then I will have B, SK, and then I will have C, KJ. Now I am on the safe side. I can flip this out because now it depends on indices I and J, but the counter of the sigma is K. There is no K dependency here, so I can pull it out. So then it becomes sigma, S goes from 1 to N, AIS, and then I will have sigma, K goes from 1 to P, B, SK, and C, KJ. What I want you to do for me is to write something for this. Can you do that? So I want you to say something. What can I write for this? It's a sigma in a famous sigma. A combination of this sigma should be famous for you. That's a product, yes, but how should I write it down? No clue? Pardon? I couldn't hear you.
Oh, couldn't you move
No, I'm just talking about this. I'm not moving anything. I'm just saying that what can I write instead of this combination?
the product of B and C?
Which entry?
The S and J.
S and J. Yes, that's correct. That is B, C, S and J. That's correct. I want you to feel it. I don't know how I can teach it in a different way, but hopefully you understand what I mean. This seems a good product because you see these indices are the same in between. Yes? And then what can I do here? I would say that this is B, this is S, it starts with S, it ends with J, and the middle one is the counter of the sigma, and the upper limit is exactly the number of columns of B, or equivalently the number of rows of C. You see, the number of columns of B is P, the number of rows of C is P. So that's exactly in the right combination. So what I can do, I can write it as B times C, but S jth entry. Okay, so let me write it down now here. So this becomes sigma, S goes from 1 to N, A, I, S, B, C, S, J. Now can you tell me and finalize the problem? What is this one now? You see, I have a sigma and two matrices with indices, and this middle index S is equal, and that is the counter of your sigma, and the top one is actually the number of columns of A, or equivalently the number of rows of this. So that's an appropriate combination exactly. So can you tell me what can I write? This is definitely the product of A by BC, but which entry?
I and J.
I and J. So finalized. So that is equal to the left hand side. My goal was to show this equality. It was a little bit playing around with sigma, flipping in, flipping out, but everything works fine. This calculus this calculation, this algebra, arithmetic, I would say, I want you to learn, okay? And of course, most of the time we use these properties, but this is the proof. And you see that the crucial part was this part. Yes? And by the way, this is very interesting. It is. Do you think that associativity of addition is also playing a role here? Because associativity of product of numbers definitely plays a role here, because I took this pair of brackets from around the first pair and put them around the second pair. So this is associativity of a product. But do you think associativity of addition of numbers also play a role here? So assuming that you lose associativity of addition, but you still have associativity of product, of multiplication, sorry. Do you think something will happen to this theorem?
Should, because when we're calculating the entries, when we're multiplying, we need to use addition, right?
No, which one I am using addition? Yes, somehow yes, but if I want to have it more transparent, even for myself, so I think when we interchange these two sigmas, you see, the order of the sigmas, when I interchange them, I think this property relies on associativity. Let me just check it. Let me just go to an empty space and I will come back to it. So when we say sigma and another sigma, so let me have I from 1 to, let me make it simple, 2, j goes from 1 to 2, a sub I j, and I claim that this is equal, if I change the order, yes, let us see why this is indeed correct. Because if you start from the left hand side, for example, you open up the first sigma, let me see, sigma I goes from 1 to 2, and then this becomes I1 plus I2, yes? And then I open the neo sigma, it becomes AI. No, but it seems it doesn't rely on that. It becomes a, let me see, it becomes A11 plus A12, and then A21 plus A22. So I am not, so here this is the addition. Yes, of course. Okay, so you see here I am just adding in this order. If I want to change the grouping, then it means I am using associativity. But what can I do for the right hand side? What can I do for the right hand side? If I want to do the same thing, I can write it from the inner one. Again, it becomes A1J plus A2J, and then I put J equal to 1, it becomes A11 plus A21, and then plus A12, A12, yes, A12 plus A22. So you see, I am using, yes, here I am recollecting terms. If, of course, at the end of the day, I will have all of them, but in different order and in different grouping. So commutativity of addition also plays a role, because I am interchanging these two and I am changing the grouping. Yes, so it means commutativity of addition, associativity of addition plays a vital role when I want to interchange the role of these sigmas. So it might be hidden, but it is possible. Actually, it relies on that. Yes, hopefully you understand what's going on. That was my, I was just thinking loudly. So because associativity of a multiplication is very transparent, I am using it. but it might be hidden that I am using commutativity actually and associativity of addition of numbers, which is a little bit hidden, not very transparent here in this case. Okay. Now, I have given you a remark. Let me just read it for you. According to the last theorem, to multiply several matrices, it is not important which multiplication we do first, but as far as we respect the order that the matrices appear in the product. For example, let A, B, C, and D be matrices of all of the same order, because I want to guarantee the product is defined. One can calculate this product in any one of the following ways. It doesn't matter if you prioritize this product and then this product, or you write it in that way, or you write it in this way, or in that way. All of them are the same. But of course, if you want to convince yourself, it's also an interesting topic. It's an interesting exercise to see why, as based on purely associative arguments, okay, why these two are the same. Why this one and that one are the same. Because associativity deals with 3 matrices. When you want to talk about 4 matrices, at each step of your argument, you need to use associativity between 3 matrices. Okay, so that's also a very nice problem if you want to think. Try to convince yourself that all these products are actually the same based on associativity of 3 matrices. Okay, but this is important. But we cannot calculate this product as, for example, like this. If I ask you in the exam or any question, calculate this, if you prioritize the product like this, that is totally wrong, unless you know something about commutativity of B and C, which usually you don't. Okay? So here, if you calculate this, it's wrong. You see, the order of reading from left to right shouldn't change, unless it is guaranteed it's commutative. Here, the order that I am reading is A, B, C, D, but it is A, C, B, D. Okay? They are not the same. So you cannot use this to calculate that. Okay? So the reason is that in the former expression, see, I'm just told you what is happening here. Okay. So there are 2 problems left. I want to give you a little bit of time to think about them, and then we come back and solve them. So one of them is here. Can you solve this problem and just give me the answer? I will pause the video at this point now. Okay, so here, first of all, tell me, what do you expect? Because you know that I have written it as a number. Do you agree with this, that this 0 should be a number rather than of a 0 matrix? Do you agree about that part yet?
Yes.
Yes. Why? Yes.
The final matrix we get becomes a 1 matrix.
1 by 1 matrix, yes. Because this is a 1 by 3. This one is 3 by 3. This one is 3 by 1. So this one and that one are gone, 1 is 3, and this one and that one are gone, 1 is 1. Okay, so it is 1 by 1, and every 1 by 1 matrix is identified with its entry. So it means that if you ask me, is it a number or a matrix, I would say rather it's a number than a matrix, okay? And how many products are involved? 2 products, this one and this one. But you see, I have been a little bit careless, or am I allowed to do that? There is no pair of brackets. Am I allowed to write this product without any pair of brackets around them to prioritize which one is first? Yes or no? Yes, because we just showed that a product of matrices is associative. So it means that you don't need to be worried in which one you have to give the priority to. It doesn't matter. For me, it's easier to because later there are many times that you have to multiply a matrix by a column matrix, so that's most of the time easier for me to do it from here. It doesn't matter. So I will say that I will first interpret this product as this one. It doesn't matter. You can test it. Of course, that's a very good idea to test it. I am doing it by prioritizing this product. You can solve it at home by prioritizing this product. Then the answer should be the same at the end. So this is equal to 0. Okay, so I will copy paste the first matrix for the time being. And then I start multiplying this. I decompose these two rows and each row by the column, yes? The first one times the first one, the second one times the second one, the third one times the third one. And I have to add them. The first one is 2x, the second one is 4, the third one is 0. So the first entry is 2x plus 4. Okay, I will take this one, multiply it by that, it gives me x, multiply this by that, it gives me 0, multiply this by that, it gives me minus 2. If I add them, it becomes x minus 2. And then I multiply 0 by x, 0, 2 by 4, 8, 4 by minus 1, minus 4, so it gives me a 4. This is supposed to be equal to the 0 number. The next step, I will multiply this row matrix by this column matrix, meaning that multiply this by that, it becomes x times 2x plus 4, the second one by the second one, and the third one by the third one. And of course this is just one number, but I don't write it as a number because that's one by one. I identify it with its own entry, so that would be my equation. And then let me solve it. So it becomes 2x squared plus 4x and 4x, it becomes 8x, minus 8 minus 4 is minus 12, and then I divide by 2 to simplify the numbers, and then I solve that one. So if you solve it, it's minus 4 plus or minus the square root of this one to power 2 is 16 plus 24 divided by 2. Okay, so it becomes minus 4 plus or minus the square root of 40 divided by 4, but the square root of 40 is just 2 square root of 10. And then divided by 2, so it means that the answer is, if I factor a 2 and simplify it, it becomes minus 2 plus or minus square root of 10. So these are the numbers that we were looking for. Okay? No questions? Now the next question, I have intentionally given you a little bit big matrices and determine the entry on the second row and the third column of this product. Of course this is tedious. You can start multiplying them by any combination, by any grouping that you like, and then just go and read the entry on the second row and the third column. But there is a simple way to do that. Let me remind you about the formulas. Do you remember I told you if you want to take the ith row of a matrix Mn, you calculate the ith row of matrix M and multiply it by the whole matrix N. Okay, and then we had something for columns as well. Do you remember? If I want to find the jth column of the product, you take the matrix M as a whole and multiply it by the jth column of the matrix on the right. And if you are interested in the entry Mn of Ij, you can take the ith row of M and multiply it by the jth column of N. Yes? So I have already talked about these things. So here in this problem, what I'm supposed to do, I am considering this product. I am interested in the entry on the second row and third column. So second row and third column. But that's a product of 3 matrices. I do it one method here, you do it at home in a different way to learn better. So I prioritize these 2. I would recommend you to do it at home by prioritizing these 2. It doesn't matter. Okay, now this is one matrix, this is the second matrix. I am interested in this entry. So it means that according to this rule, I will take the second row of the matrix on the left and multiply it by the third column of the matrix on the right. Okay, and now this is the column, the third column of a product. I use the middle one. So this gives me the second row of A and then this will give me the whole matrix B multiplied by the third column of matrix C. But I cannot simplify it more than that. But this is also good because now the second row is just this one. I don't need to consider the whole A. It becomes 1 minus 1, 1. And then I multiplied by the whole B. Unfortunately, that's inevitable. But it's better than multiplying all of them. And then just the third column of matrix C, which is 2, 1, 2, and 1. Okay, of course I expect you to do this one, but let me also teach you something. I think this is also good to learn how GeoGebra works with here. Of course I gave up using Classic 6. I would prefer Classic 5. I don't know why I actually updated to that version. I believe this 5 is working better. So here let me write matrix 1, M1 is equal to, and then the first matrix, you need to know how to put the matrices. So I need to put curly brackets in both versions, actually, it doesn't matter. And the first matrix is just one row matrix. So it is 1 and comma minus 1. I need to write them as lists. Oops, I have to put another curly brackets around these two. Okay, so this is my matrix M1, and then I have another matrix M2. So this is a little bit more numbers to type in, but just let me do it quickly. I have 3 rows, so I have to open 3 more curly brackets here, and then I will have 1 comma 0 comma 2 comma minus 1, and then the next one is 1 comma 1 comma 2 comma 1, and the next one is 1 comma 1 comma 3 comma 4, and then this is my second matrix. Okay, that is there. Okay, and then another matrix. Let us just finalize this hopefully, and that is a column matrix. So it means that this is equal to 2 curly brackets, but then the first curly bracket gives me 2. The next one is there only one entry here. So these are the rows actually in GeoGebra, and even in more advanced programs I think you can use this way. Okay, and then the syntax should be the same, I think, here. Okay, and now I have these matrices. As you see, now my goal is to multiply them. I don't know if the syntax is just this symbol. Let us just check our chances. Okay, oops, no, that's M3. And now, yes, of course this GeoGebra keeps this curve, these brackets around that. So that number, if I go back, is 10. So this number is actually 10. But I want you to confirm that by calculations, and I want you to do it the other way around by prioritizing this. These things would be a little bit different, but what you get at the end should be 10. Any questions? So I think it's also good to start working a little bit with GeoGebra, because matrix calculations are messy and computers are very good at it. You can also write your own code if you have knowledge about some computer, I don't know, some language, coding language. I think it's a very simple task. So you can start writing your own codes. Okay, no questions? Thank you very much for listening. So I start